Mhm. And I think in life, so mic test one, two, mic test. Um, let's monitor things. Wait, and we are live. So, okay, so today I plan to try to figure out why pole is OM and equal is O1. Yeah, so at any point in time, if you have any questions, feel free to drop in the chat or join the Zoom, join the Zoom and just voice out your question. Um, yeah, so without further ado, let's look at the kernel source. So I think the best place to begin, usually for kernel source dive is, in my opinion, the best place is to look at the syscalls. So yeah, so let's try to understand why let's try to understand entry point basically. So usually the format this the format for system the kernel syscalls will be of the form it be usually of the form syscall define syscall I think, or is it syscall define? No, it's the other way. Syscall define, and then the number here will be the number of parameters. Um, yeah, the number here will be the number of parameters, and so we're looking for pole and equal, right? So I think pole, in order to check how many parameters pole takes up, we can do a man. So man pole, and you can see that based on this, pole takes up one, two, three parameters, right? And how about equal? Equal takes up equal takes somewhere what's the yeah, somewhere with the function signature equal 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 cutoff. I don't equal if I think it's here. Yeah, equal takes up okay, maybe I should do equal cutoff. I think it takes up four, right? So we can take a look at system define tree code perhaps. And yeah, we see it there. So let's keep this in view. This is poll. It's under select.c. The difference between select.c and poll is that select is a bit older, so people generally recommend using poll. I don't think there should be a good reason why you're using select. And if you look at epoll, epoll is four parameters, so the system is called define for a no, should be, or is it one? Okay, one is for create, two, three, four, oh, four. Okay, and I guess there was the six. Yeah, I guess it's four, but it's not really equal. It's more of equal cuddle. Yeah, I was searching the wrong thing just now. It's equal cuddle, and this implements a controller interface. Well, I don't think this is the exact. I think what we want is equal weight. Right? Equal weight is the one that will wait um for descriptors. Yeah. So my friend just sent me a text message. Let's try to I'll paste it here and see what we can decode of it. Thanks to thanks for sending it in. Let's see. Select users a bitmap. Usually 1224 long. Takes in the file description you care about, and index of that bit is one. Thanks the file descriptor. Okay, right. Okay, that makes sense. So the problem is if we want there's a lot of unused space. right? Okay, thanks for that input. So poll is basically an array instead of bitmap. Okay, great. So that kind of explains why we use poll over select because poll is superior, uses an array instead of a basically a Boolean array of size 1, 0, 2, 4. So yeah, and both require copying of these arrays in from user space and kernel space, and scanning through everything. So okay, and for epoll and queue, there's a red black tree with log n CRUD operations. Yeah, so I think at the core is we're probably gonna explore this later, but there at the core is a different data structure. So once the file is ready, a callback signal, it cannot adds the file to ready queue in O1. Black tree is still needed, so okay, yeah, thanks for that. Thanks a lot. So let me just put that aside. Yeah, so continue here. Once we find the once you find the let's turn down the aircon a little bit. Start cold. So once we find the syscalls, we can then proceed with the tracing the kernel source. So yeah, so in this case, okay, so let's take a look at poll first. I think poll might be easier to understand. So system define tree poll, and we see that so what does this poll take? It takes in a poll FD, which is FD events and R events. Um, so it takes in a struct with these things. Give me a moment, unless something is a bit broken. Um, um, let's try to feed this into your house. Then the thing broke. Okay, it's back here. Let AI do its thing. But in the meantime, I believe this is what the user passed in. UFDS is probably this is probably an array of a why is there a comma here? Uh oh wait sorry wait, did I insert this comma? I don't think so. One. Okay, sorry. This is the type. This is a macro. So the way you define the macro is that you take this as a type, and then this is the name, and then this is type, and this is name. So in this case, we're having an array of OFD structs. We can call it UFDs, and the other one would be into the number of file descriptors, and last one would be timeout. So we can see that if we see what the so yeah, pointer to array of FD structures. Each pole FD describes a file descriptor to be pole. Um, yeah, so I think without going into too much detail of what this is, like I don't really know what our events is for. But yeah, basically this takes in the file descriptors that the user wants to pull on. And we can see that we have a poll select set timeout. Okay, that's just setting timeout. And basically the bulk of this is going to be in do sys poll, right? So often this is kind of the pattern of kernel code. There's some syscall and uh, there's a lot of nested there's not like nested function calls. Yeah, so let's go into this. You see that this is the okay, so we see that um okay, so we see that there is a table over here of whole WQs. There's a poll table, right? I think that would be an important structure for us. Then there is a task chart and so on. I don't think let's revisit it later this time, but let's try to look at the bulk of the code. So, okay, yeah, so I think from here we can see that now we're copying from the user, right? We're copying from we're trying to copy from the user the array that he passed in, something minus to do. I think to do is okay, so to do initially is this. Um, okay, let me check the function signature of what uh, so I believe this just copies. I don't think this is just anything very fancy. I think this just copies it, yeah, from the destination, from the source and the size. So, okay, so um, basically, we are copying into entries, uh, and the source pointer, I'm a bit confused by why they do minus to do. So initially to do, okay, so I guess to do, initially to do is FDS, right? So, that will mean that this is 0. So initially you're just copying the first element of user file descriptors. And how much are you copying? You're copying the size of OFD, um, or size of this times the walk length. So, mm, yeah, I don't really know what the length is doing over here. Let's see what AI says. So, it's a number of bytes to copy. How many OFD structs are there in this chunk? Okay, so it seems like we are copying chunk by chunk. So we're copying chunk by chunk, and if it's copied successfully, then it will go to this place. Um, it will, what it will do? It will, um, this entire chunk will, let's see, allocate a small arguments on the stack to save memory and be faster. Use long to, okay, so after copying this, there is probably somewhere where, they actually do the whole way thing. I mean, I think it'll be probably Dupo, right? So yeah, so I think this is just copying the file descriptors in um from user space to kernel space. I the details kind of seem a bit confusing to me now. Um, but the bulk of it is that after we've copied it in, the table we would call Dupo, and poll list will be a linked list. You can see it's a linked list of it's a linked list of entries, and um, each entry will probably have some information about the file descriptor that we're pulling on. Pull work queues. Is it work queues? So this structure, as you can use, is manage state and resources. Um, is it called wait queues, I suppose? I'm thinking it's wait queue because the name here suggests that it's wait. So yeah, it seems like it's an init wait and then you pass in the wait queue. So yeah, wait queues. Okay, sure. Okay, so we pass in we pass in the wait queue, and the end time doesn't really matter. And from here, what do we do? From here, there is you can see quite clearly do MD is the bulk of it. I don't think the rest are very important. I find like I mean, most of the time when I trace kernel code, it's really just most of the time when I trace kernel code, honestly, most of it is just a lot of checks, a lot of edge cases, and the bulk of the code is usually just a lot of interactions away. So yeah. So looking at this, you see that fish for events, and I think this is a for loop that walks down the poll list. Um, yeah, it walks down the poll list over here. Uh, yeah. So for each entry, so let's say walk. Okay, so let's see the list that we pass. The list that we pass is here. Um, so walk goes to the list. Initially points to the head of the list, and while walk is not now walk. Yeah. So this is clearly a this is a for loop that goes through the linked list of POFD shrubs. Sorry, of PO list nodes. And for each one of them, POFD we get the entries will tell us if entries will be a pointer to the POFD, which is what we get here. Um, PFD is the POFD, and the end is the end is just this is the I think walk dot length is probably the size of the size of the entries over here. Um, yeah, it's probably the size of the entries over here. So yeah, moving on. We initialize it like this. PFD. Well, we haven't hit the end. Okay, so there is so just to be clear, the whole list has is a linked list itself, right? Um, it's a linked list, and then each node in the linked list there's an array. It's an array of OFD um, objects, right? OFD shrubs. So over here, the for loop over here is walking through the list, and the for loop over here is going through the array of OFD in that list. And so for each one, we do we do this on PT. What is PT? PT in this case is whole table. So there's a whole table, um, and okay, so I think over here we might be nice to have a bit more context, but we call do poll FD on this, and um, yeah, so I think over here um, the thing to dive into is poll FD. Do poll FD. So this is switch for pollable events on the poll FD file descriptor. Okay, so the POFD struct, right, it will contain POFD struct. It contains the file descriptor, right? So we're only interested in events matching PO events mask, and the result matching that mask is was recorded in R events. Right? So that's where there's not mask AI. R event stands for return events. Um, and the P weight PO table will be used by the MD provided PO handler for waiting blah blah. Okay, so I think there's a few things I need to learn over here. One would be what is a poll table. One thing I'm quite unfamiliar with would be what's a poll table. Another thing would be um, yeah, another thing would be um, mm, I'm a bit confused why. At the moment, I'm a bit confused why we have okay. I think the major thing I'm confused about is a poll table. So yeah, so let's take a look at what that entails. So we get an FD, we take a mask, do this. Okay, FD get is in file.h, and FD get this is a header file, so that's not what I want. In fact, I want FD get. Let's see what that is. FD get. Let's try to search a signature. Okay, so FD get. What I want is the C, right? The C one. So there is this. Because FD get light, more interaction. So Okay, so over here, this is where a bit more, this kind of intersects with our open file table, that kind of like, if, we intersects a bit with other, the storage, the virtual file system knowledge. So we see that it's empty, get fget light. Um, so okay, so this is, yeah, it's just this. So the current is the current, I believe this is the current process. Um, I believe this is the current process. Let me just verify it. Um, current process files, the current task. I think at this current process, it gets the files, right? So there's a, yeah, so it's the current task, the process or task that used interchangeably. And one of the, in each process, in each, um, in each process, there is a file struct which stores the open file table, right? So it looks at the open file table, it gets the open file table, and in this case, it looks up the MD raw. This is just, uh, this is just, yeah, okay. So this is just array index mask nose spec. So it does some RCU dereference. Basically, this is a glorified dereferencing the pointer, with RCU, yeah, with RCU tracking in some sense. We don't know what RCU is, it's just a locking mechanism. So it just prevents race conditions basically. So in this case, basically you can think of this as just a glorified style, like the reference operator, or rather it just, yeah, it kind of like locks, locks it so that you would not, yeah, you can just think of this, you can just ignore this RCU stuff for now. Um, and okay, there's a mask, then need masking, column assertion. Okay, let's see. Okay. So actually that wasn't the main one. So, um, oh, okay. So I think if there's only one file, then you just get that file. And I think that's what this is getting at. But if there's multiple files, then you need to call fget files. And then that will call get files RCU. And then this is a loop that will the file table. So basically, fget just gets the whole point of fget is just that it oops, sorry. Uh, the whole point of fget is just that this gets the file from the file descriptor. So yeah, and this gets the file from the file descriptor. So I think f in this case is mm, what is this? Okay, maybe I should ask, yeah, before I learn wrong things. So f in this case is a fd. So represents an open file descriptor in a safe and um, yeah, so we're not actually getting the file. I think we're not actually getting the file. I'm a bit confused here because why is from SD is basically just a glorified number, right? Like, yeah, I don't really know the point of this. I'm sure it's just some kind of type checking thing. But okay, so MD file over here. This is the thing that um, okay, yeah, so this is the thing that converts it from, yeah, this is the thing that converts it from from a MD into a file, right? So there is something going on here that I don't really understand. I think this kind of ease into the file system, starting file system, but let's try to ask AI. Let's begin with Yeah, so it's a macro that extract the pointer to a control file from a FD variable. So, um, oh, okay, okay. Let me ask you this one. So, inside down below. I think it's some kind of optimization, right? Okay. So I think this kind of makes sense. So basically they're using bit tricks, right? So if they just store, yeah, because the lower few bits of a pointer, um, yeah, because if your struct has a certain size that's multiple of the size of power of 2, then the lower field bits are always, the pointer to that struct will always have lower field bits goes to 0. And you can use those 0 bits to store extra flags. So if you put this in a struct, right, then you'll be unable to, you'll be, because of struct packing, the way they pack the structs, you'll be unable to have you have an unnecessarily large thing. So this is more of a struct packing, info packing kind of thing. Um, and yeah, basically this one they end it with this one. So they end it with this is bitwise flip, right? I think. So they do this and this, and I think this is one and two. One or two, bitwise one or two is just going to be um, 1 1 3, and you flip it around. Okay, so basically this one just gets the most significant bits, right? Leaving 2 bits, the last least significant 2 bits to 0, and converts it to the file struct. Um, yeah, and that's cool. Okay, let's see struct file. What struct file contain? Struct file in fs.h contains yeah, all these things. So okay, I think that's kind of reasonable. Um, yeah, okay, I think this kind of reasonable. Okay, sure. So VSF poll, FD, this now has a pointer to a file. And yeah, so now this is pointer to a file and file. So here the difference between a file table and open file table and file. So I think let me just call. So there's this nice picture, I guess. Yeah, so the key difference is because of something like that. So there are 3 system file tables. Each process will have some file descriptor table, which are small integers, and they'll be mapped to open file table with some kind of which points to inode table. So in this case, there isn't an actual inode. I don't think so. Um, yeah, I think the open file table can possibly point to sockets. I think that's what we'll see soon. Um, yeah, so VFS pool. Okay, so this is the part where we kind of go through what we call C-style polymorphism. So as you may know, how implements how C++ implements the uh, polymorphism is via a vtable pointer, right? A vtable of function pointers. So if you have an animal that can make sound, and you have a cat that overrides it, and the vtable point to the cat's make sound. Um, so basically, at the core, right, it's all just function pointers. So because in C we don't have uh, we don't have classes like the same way as C++, we have like inheritance. The way that C does polymorphism is the way that C does polymorphism is via function pointers manually, right? So every file in this case, this file is kind of like the 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 parent, right? The base class. And there's many implementations of this file, and how it's kind of implemented is if you so imagine this is struct like animal, right? And if you want to implement uh, a derived class, then you will be let's say if you want to you want to implement a cat that is an animal, and if you want to define um, a sock that is a file, then what you will do is you will fill up these function pointers. You will see that few of these are the the file operations in this case. You override you have these function pointers, right, all point to your own implementation. So this is basically a table. Um, yeah, so this file operation struct, um, what is it? Fop, that's file operations. So you can see that in this case, we have as poll, there's fop from here, file fop, and it calls poll. Right, so now when we get poll, there are a few implementations of poll. So this is where we can um, have, I know that this is under sort poll, right? So perhaps if you do not want just sub poll, you can, I guess one way would be to do like dot poll equals to, and here you can find all the various implementations of poll. Like, so for example, one thing that we might be familiar with is if you have see this. So for example, if you are implementing a GPU driver and you would have the GPU driver exposes control the GPU via some kind of files, then this will you have you implement in order to inherit the struct file, you have to define your own file operations pointers. And one of this is this, right? So what we're interested in this case is that is sock. So for example, if I think files include I do net, right? I do net, then I'm only restricting myself to net drivers. So net, yeah. So you see over here, it's I think what I'm looking for is AFB sock, or is it? I think there's one with the sock. Or, um, sorry, sock. Let me find it. Not BT sock, but sock. So the not sock. Wait, but sock. Where is it? Where is it? Sock. Or is it just be sock? Oh, I'm searching within that. Yes, that one. Okay, so it is sock. But so here's the sort code I'm looking for. Let's see where it's about functions. Yeah, okay. Okay, this is great. So I found it. So yeah, over here you see that in net socket.c, which implements the sockets, which implements the socket derived class. Socket in some sense socket uh, derives from base from the struct file, right? So socket is a type of file, right? When you write to a socket, you're writing to a file. So this is where the socket file ops are used, and you can see that they are used over here when we do socket log file. Okay, so basically, this socket file ops represents all the functions that will be called if you do various syscalls on a socket. So if you do an mmap, you call this. If you do a poll, you do this. And yeah, so in this case, poll is the one we're interested in. So this is the one. We're interested in what happens when we do poll on the socket. So there's some okay, so there's some private data here, stock ops. So once again, there's a bunch of proto ops that I think this refers to protocol ops. Yeah, let me ask ChatGPT what is protocol ops. I believe these are all the protocol, yeah, protocol operations, right? So if you are implementing a socket, I believe you can yeah, you can support the family over here. So what families and which one corresponds in let's say TCP yeah, which one corresponds to TCP and IP. I think in this case so yeah, so IPv4 will be AF INET. Um, okay, so in this case, I don't think okay, so TCP and UDP is not a family, but rather these are trans. Okay, okay, so this is more of IP versus others, right? Um, so besides, right, so which layer of the OSM model is this? I think it should be like layer three. Yeah, this is layer three, definitely layer three. So AFINET for AFINET 6, the socket type, whether it's a string, diagram. Um, okay, so I think if so, users, yeah, so the socket family is a layer 3 concept, and the socket type is a layer 4 concept. So in this case, we are dealing with in the product ops family only refers to layer 3. So, yeah. So, so that's great. So yeah, so you can see that product ops accepts a whole bunch of stuff from here, which is nice. But we're curious what happens when we do poll, right? When we do poll, it calls ops, right? Which is just sock ops poll. So basically, what this means is that each family, each socket family, will have their own implementation of poll also. So there will be I'm guessing there's IPv4 for poll, it's IPv6 poll. Let me just double check that. No, oh, there's no separate. I thought there'll be two different. Okay, so I was wrong there. Sorry. Um, okay, so maybe I can ask. So, what are some important reflections? Total policy, policy. Um, INET stream ops. Okay, so AF INET. Suppose that will be here. Um, total. INET stream ops. Okay, so stream between these two is more like yeah, so um, um, okay, so there is a difference. I'm a bit cold. Let me just go and turn down the aircon a little bit. Yeah. So it seems like there's a TC pole and there's a UDP pole. Raw socket, Bluetooth socket. Okay, yeah. So it seems like TCP um um 5.6 thinking is the same with TCP also. Actually, it's gonna be a nice chance to revise what it means to be the different units of CPU, IP. Is there UDP and IP? So I think so. It's probably a nice start. This is what I'm looking for. So then mention later. Yeah. So if you're going to talk about socket can on a small scale UDP under IP. Um, okay, right. So it's UDP versus the English different. Right? So okay, back to this because pole and the exact pole that you call will depend on whether you're TCP or UDP, right? So in this case, if you're interested in TCP, then we'll look at TCP pole. So we look at TCP pole. Let's see that it's used in IPv4 over here. Right, this is INET field ops, and it's also used in IPv6. Right, it should be if there's some IPv6 around here. I don't know why there isn't, but let's take a look. I'm kind of curious. IPv6 should have its own AFI net too, right? Um, what is it? Um, so this is a bit off tangent, but so, yes, there are net 6. I can see that. There should be the TCP pole too. Yeah, okay, so there is a TCP pole. So TCP pole is implemented TCP, which is under IPv4, but I guess they are kind of reusing the IMAP 6 should include some of the IPv4 headers. The, um, it should include TCP.h, right? So yeah, okay, so this is the TCP pole. Okay, so now we are on TCP pole, right? Um, and I think this is where it starts to get a bit juicier. Let's see. So what does this entail? So TCP pole takes a file pointer. Um, right. Takes a file pointer. What actually? Okay, so we still have a pointer to the file that we are holding on. Um, what I'm a bit confused is why we have a sock. You know, like why do we need the file and the sock? Let's see what it uses. So if I see, wait, so if I take a look at across all these junk and get value that ops one um stop it. The front ops one. Yeah, okay, so this socket C. So then here we pass in the sort and the file. But over here, so here at this level at socket C is where we extract the sort, right? Like sort code takes in the file and so if I do I can use file ops home. Now if I do ops home, no, like there's something else. What comes before that? Actually is FD. No, F, I think it's F ops. Yeah, okay, so, no, F ops poll, no. There should be a software. Soft poll equals the soft poll, no. Equals to, no. I think I lost it. Um, where is the use of soft poll? Um, okay, so let's think about this. Socket, what we call soft poll, something that has poll, right? So something that's poll, that will be in the file operations, right? File operations and sock file ops, sock, yeah, sock operations. So this is where we have a pointer to this, and now we've come to this where this yeah, so it's a file operations, and in this case, what we call file, I think we call it. So this is one layer. Um, there's a is it um, and we pass in a file layer. So um, hmm, I think it's this. No, I don't think we quite right. But I think it's maybe this time I'm allowed to rewind unwind the. Oh, you know what? I'm just gonna go all the way to the very start. Where we have when we found um select.c. So the VFS code which does here was where we did it. Right. So this is the first place where we did it. So yeah, so we do VFS code on it, and then so what kind of file are we? So from the very beginning we already have, so from select C, we call VFS code. Okay. So once again we have the file descriptor over here. We have the file descriptor, the list of file descriptors, right? Um, sorry, no, this is one file descriptor, right? This is one file descriptor that we're calling on, and then we the file descriptor gets converted into a file, a short file, right? And then we call VFS on it. VFS poll takes in two parameters only. Once again, we still don't really know what the poll table is. I'll try to study that later. But we call it this, and for the file being a socket, right? The file is a socket in this case, then the file operations would be a socket operation, right? So, um, yeah, so then because the file is a socket, if we do sock poll, here's where we extract out the sock, right? And how we extract out is via the private data, right? This is where we can store additional information that's um, unique to each device class, right? So we then call poll, which in this case we call poll, which in this case is implemented by what was it again? Yeah, like that. Um, yeah, this one, which used the TCP poll. Right? So TCP poll is the thing. Um, and what is it called? So TCP support. I believe this one probably does some kind of casting logic again. TCP socket. So okay, so here is where we come back to the difference between socket and sock. So um, yeah, I remember trying to study this before. So we see, I kind of forgot the details, but sock and socket are kind of related, but also not really. So socket is a pointer to file, pointer to sock, and proto ops, right? So socket is socket. Yeah, so that's a socket. And what is sock? Sock in this case, this is the way of doing C style um, inheritance. Uh, so a sock in this case seems to be a bunch of queues, it seems. Queues, bunch of queues. Um, okay, but what is probably critical is called sock pull weight. I don't think the rest of the parts are that important. And more importantly, we call sock pull weight. Sock pull weight. Um, okay, so these are the important files in this order. Um, sock pull weight place memory barrier, whatnot. Then we call it pull weight. It goes back all the way here. No, I don't think that's right. It doesn't seem correct. I think, okay, I think it's more software with place memory barrier. I don't think this actually does any weighting. Let's ask ChatGPT. I think what actually does the polling in this case is the INET CSK listen code, which is nothing much, I think. Uh, doesn't seem like it's much. Oh, okay. I guess this kind of meets the queue, right? Like there's some kind of memory on me here that I will gloss over because I don't really want to deal with complexity now. Okay, okay, so this is where the wait queue happens. So this is where the wait queue happens. The wait queue happens over here. So it does kind of, um, okay, let me just ask this entire segment what it does. Um, feel free to leave some comments in the chat though. I just realized that you can't really see the AI comments. Can you? Um, or I think you can. I don't think. Yeah, okay, you can. You can. If I go back to this, um, okay, let's see what this is about. TCP pole is a function that implements a pole for TCP sockets in the Linux kernel. Um, okay, okay. Yeah, I'm a bit confused. Why is it, so it's not implemented at the sock level? Okay, I'll just accept it for now. Um, yeah, TCP pole. Okay, so let's see this. Especially the socket polling implementations. We mentioned that when a process is waiting for events in socket, the weight is set up correctly. Oh, but no, I there's not the one that one. Yeah, okay, so it's called when user space calls poll. Okay, okay. So function signature poll table is the registered interest in the class. Um, so sock poll weight. What is sock poll weight actually do? Um, I think this is where we kind of come into the poll table thing. Um, registers current process, we will cannot if the state of the server changes. Okay, so if register, this is where it registers something, right? This is necessary for efficient waiting, so it will sleep until then. So where exactly does it do the sleeping? I'm not super sure. Um, okay, but after that, it loads the current TCP state. Um, so you just ask the AI, soon as it review at stop or wait, does it review at stop or wait? Um, it does not use. It registers the current processor waiter in the wait queue. Um, it sets up very functional. Okay, so after okay, I see. So this just does a registration. It's only after all the file descriptors have been done this way, then we go to sleep. So let's find where that code is. So this kind of just registers the code back, registers the registers the waiter, right? Um, let's see where try to see where I actually do these kind of all mangled up right now. See this code, this DLS code, file opto, um, file opto, opto TCP. Wait, what was the part where okay, so okay, what I'm looking for is do that before, right? Um, yeah, so here, after it's done, then I'm guessing somewhere here, is it this? Let's try to ask. So here, okay, okay, sure. Okay, so that is where we do the poll schedule timeout. Okay, so to summarize, when I do poll on the set file descriptors, it'll create some kind of linked list and walk through the linked list through all the file descriptors. And for each one, it'll register a waiter. Right? For each one of them, it will call a whole bunch of indirections. And at the end of the indirection, it'll register a waiter. Right? So a register waiter, um, oh here, this is where it registers waiter in TCP port. It goes all the way into TCP port. Then after that, it will yield, right? It will yield the post schedule timeout. Timeout being um, yeah, so it's a hardware it's a timeout so that if it expires then we will connect. So the yield control. And after that, then we read the state of the TCP and then we do the poll. So if it's been yeah, so I guess over here is the appropriate time to understand what is understand how the poll table works. Um, this will be appropriate time to understand how the poll table works. Um, so understand how the poll table works. Let's see. So I think we might want to get it here. Poll does not return true the granted poll. Uh, okay, so the poll table has already. So I think my understanding is that this is an optimization. You say that if the poll is already going to return, then you might as well not actually hold it in class. Um, the return flow is guaranteed. To exit the current polling operation is in a mode that does not actually want to wait for events, right? Okay, so basically, um, non-blocking. Okay, so is it always if the poll is not going to wait, there is no need to register the process and surface wait queue. Okay, so you're registering not a file descriptor, you're actually registering a process. Like you're registering a process on the socket wait queue. Registering not free, most okay. So skipping this step. Ah, okay, that's a great analogy. So so it's kind of like so if this process wants to register a certain if this process wants to register itself as on a certain socket, and that's why we need to pass in. Actually, no, not does the file have a pointer to the file doesn't have a pointer to how does it register the current process though? I'm not sure about that. Okay, so basically, if it does not want to register, then we return immediately. Okay, I'm not super sure about this optimization, but I don't think it's that crucial. Yeah. So whole let's see. So whole do not touch the software directly. Use access functions. The whole weight. So okay, so this is where we use the whole table's qprop. Right, qprop is a whole, it's a whole, it's a whole qprop, and a whole qprop is a function. Um, whole qprop is a function. Okay, I don't think what is your um, what is K? I think I don't really understand how trying to search out how whole table works. We'll select. Okay, let's take a look at this thing. So, obviously, applications that use non-blocking IO often use pull and select. Pull and select have essentially the same functionality. Both allow process to determine whether it can read from or write to one of the open source block routing. There are types of things using same applications. Okay, sure, multiplexing IO. Um, so on that, some implementation of Go, they often have the following. Yeah, so okay, that's good. Implementing the Go method with multiple implementations, like one for each file type. Um, for the following prototype, driver's method will be called whenever the user space program. Yeah, so file system driver method called whenever users involves on the device is in two steps called poll wait on wait queues, right? So what is a poll table wait queue? I don't really know yet. Um, so both of these versions are really straightforward. It's very similar from one driver to another, however they vary now. Okay, so they all um, so a poll table structure. The second argument will, yeah, that's the thing I don't understand. Um, is used by the kernel to implement pollinators on select systems. We declare in poll.h, which must to driver randos, and the kernel needs to be something check spark the driver methods in the only event queue that could wake up process and change the status poll to be adapted according to poll. Okay, so let's see this. Must use as a bit. So the poll table is passed to the driver method for poll, so that every event queue that could wake up the process and change the status of poll operation. What's that mean? Um, I don't really understand. Um, I think what this means is that every event queue referring to this, that could wake up, it can register itself. I think. Um, let's take a look at the over here, the calls poll wait. Okay, so calls poll wait over here. So this calls poll wait. That's what we're seeing here. The second task performed poll wait queues. There's essentially a hierarchy over here. That's not um, poll wait queues. Okay, so poll wait queues will have a poll table as well as a poll table page. Okay, okay. Okay, sure. There's something like introducing, but it seems that I think the Chinese convention might actually be kind of helpful. Um, okay, I understand now. Uh, okay, great. So I think I kind of understand what's going on here. A whole table over here. Actually, um, maybe if I pass it to, I don't really, let's try to understand the whole table. How does what is what you drop? I don't really understand that you drop. Or rather, what is the initial code table that passed over? I think what I want to know more importantly is the initial code table that was passed in, right? Because they're passing from the very, very start. Like over here, right? Over here, the whole WQs are already passing over here. And that's if you do repo, right? So you search where this is used here, where is the code table created? Okay, so here the code table isn't created yet. But over here, the whole list is created. Where's the code table created? Repo, okay, there's a table here. Where's this table? This table is created here. And it's just created, initialized to, okay, so here's where we initialize it. Up there, we just define the struct, just like that. Here's where we actually initialize it. And I think, um, so this is some stuff. Okay, so the polling task is the current one. Trigger the new. Okay, so this is where we initialize um, the queue prop, right? We will initialize the queue prop. And we initialize it this way by passing in this thing and this thing. So the key refers to all events enabled. The key is not very important for now, it's for masking. But what is important is that is that this initialize this passing code weight. So this is code weight is basically queue prop. Right? Queue prop points to code weight. So where is code weight? Code weight is called there's one declaration here, there's a definition here. This is where we have like this is where this is what qprop is essentially. So you go all the way back down here, go all the way back down here. Qprop we call prorate. We call prorate. So yeah, we call this on file thing and so automatically this calls implementation, which in this case was declared over here, right, in select. So we're passing in the function pointer all the way down only for the guy that's called all the way down there um, to call for it. And it's kind of funny how we pass in so many pointers here and there, but that's just the Linux kernel for you. Um, yeah, so I don't think, okay, so anyway, back to here. Um, when the pull rate is past the file pointer, and a wait queue, and a wait queue, and a pull table, you know, of what's happening. The customer will from out of okay, okay, sure. Wait queue, function entry, poll wait seems important. Then we add wait queue. So I think this just adds the poll wait to it. So we create entry in the poll table, and then we add to the wait address. So wait address is the address of the wait queue. Yeah, okay, wait address is the wait address of the wait queue. We add this entry. We add wait, which is this. I don't know why we don't just add in the whole pointer, but we add this weight weight entry thing um here, and we are also initializing full weight. Right, so it's here declare default weight function. The default weight function is um, default weight function. Um, okay, it's already here. Okay, it's all the way in the scheduler, which I guess makes sense. Okay, so in the weight dot page there is a weight queue initializer over here, default weight function. Um, right, to wake up. Okay, that's a weight function, but I want something. I want to see uh how an incoming request or the NIC can wake um, can wake up that process. Yeah, I want to see how the incoming process can wake up the process. So this is not really what I want. Um, yeah, I study computer science for the question in the comment. Um, and it's interview season, so I need to study. Um, wait, what I'm so maybe I'm asking uh, what I'm thinking, how how press on the and how process. I don't really know if I can. Okay, so it adds to a wait queue. The link interrupt comes and the socket receives a buffer. Okay, so we're looking for socket wake async. So, oh, wow, what a nice diagram. Let's take a look. So, user process pull on socket, registers wake queue, and then it sleeps, right? And then when the link has an interrupt, um, the network step process, okay, and so on, and then it calls wake interruptible. So, okay. So in a short socket, right? I guess what I'm looking for when I do add wait queue over here, I'm looking at the wait queue head, right? So the wait queue head, so if I'm not wrong, the socket over here, short socket should have so you know, with the TCP sock omit P, P is a whole table, Q clock. Okay, so this sock over here, the sock should have um a wait queue price. There we go. So um yeah, a sock has a wait queue. A sock has a pointer to its wait queue. So when we call the event flow, okay. So there's and so it needs support from the driver side too. So I think in this case, we're probably looking at so it seems like wake up interruptible is not really just what else would you use? It seems like it's used in these places too, which is a character device. Ah, I see, I see. So it registers. Okay, so file IO is one example. Field text is another example. Uh, okay, I guess because the whole weight cube thing is in general quite a theme. Um, so why would they say this um, like where is the part where it's OM? Right? I see, I see. So where's the part where you wake up? I think it'll probably be TCP here. Right? So here we use the um, no, this isn't a web part. You know, AI is actually simulating. Um, but this is computer, yes, but I think what I'm trying to look for is the part where the before is the part where there's a for loop, right? So website here, in terms of home, select home, home, yeah, do poll. There is a for loop here. Then after the for loop, after the schedule, Um, After the scheduling, um, I'm trying to talk on reducing later or uh, the yeah. Okay, so there are two parts. Like the study around So it seems like one key difference between Poll and Epoll are that Epoll would for Poll, right, every time you do Poll select, um, you must set up the data structures and pass it in, and you know, copy it, and the kernel will go through each one of the file descriptors and add them to the RAID queue if they are blocking. But for ePOL, you are able to kind of maintain that state within the kernel itself. So if you if you are going from 1000 to 1001, right, you do not need to reprocess the 1001 file descriptors. You just need to just tell equal to add the additional one, which is why it's an equal cutter. It's equal weight. There's no, it's not a single, yeah, that's why it's equal cutter basically. It's kind of makes sense. Um, but I still don't really understand the part where there's a callback. Adaptable, let's set wake up into adaptable, super, perhaps. So it depends on it. And basketball here. What's as as always, I, mm, okay. What's all GC6? I don't know what's that. Um, she got really wonder. Mhm. See that there? Okay, that would be. So, mm, we receive SQ, so at that. We one project, this, actually, um, Let the taxi is usually the name of the driver. Receive SQB. Receive SQB. There is so what else? Find where we register. That's the letter box. About there. Um, yeah, and we didn't do the letter box. The device box. I don't really want to understand. I don't really understand the GRO kind of stuff. So I'm I'm trying to find out. Okay, so I'm trying to approach it from driver point of view now. I'm trying to see where if I if the driver refuses the socket path escape path, correct, an SKB, where it gets processed, and from there I'm trying to trace um where where it wakes up the red queue. Um, yeah, trying to trace that. It seems like just like if I just search this word, let's do this, then search this directly, um, and I can get, yeah, it's a net power here, trace, receive, exit, internal, see, and so let's go around,